As we round out our discussion on probability and statistics here in Algebra 2, we're going to take a look at the normal distribution. Now, in our previous lesson, we looked at binomial distribution. And in distributions, there are several different types. The two main categories are discrete and continuous. A discrete distribution is a distribution pattern with a finite number of possible events, whereas a continuous distribution is a distribution pattern with an infinite number of possible events. Now, with a discrete distribution pattern, if your number of events that are happening is large enough, it will start to behave like a continuous and you can make an approximation. But in this lesson, we're going to be looking specifically at a continuous distribution pattern. Specifically, we're going to be looking at the normal distribution pattern. This pattern is a continuous distribution pattern with data values that vary from the mean. Now, normally distributed items are like what are shown in this graph here. They have the mean value in the center of the graph and then items uniformly distributed to either side. Now, not all methods will be like this. There are also what are called skewed normal distribution patterns. A positively skewed item will be heavy towards the left and skew out to the right, whereas negatively normal distribution patterns will be heavy on the right and will grow gradually to that point. Your mean value is always the highest point in the normal distribution curve. Some people talk about a bell curve. The normal distribution pattern is a bell curve. So what can we do when we start looking at the normal distribution pattern? How is it actually set up? Well, let's take a look at that. When we talk about normal distribution patterns, we talk about the mean value, but then we also talk about something called standard deviation. The standard deviation is how far things vary from the middle. A small standard deviation will make your normal distribution curve skinny, whereas a large standard deviation will make your bell curve much more level, but still have a center top value. The standard deviation patterns in here is that when we move one standard deviation to either side from our mean, each side will encompass 34% of our data. So if you're within one standard deviation of the mean, that will make a total of 68% of all your data. If we move out two standard deviations, we add on an extra 13.5% to either side. This brings our total to be 47.5% of the data on either side, approximately, or a grand total of 95% of the data falling within two standard deviations of the mean. Now, if we were to take that out one step further, we will add on an extra 2.35% on either side, making 49.85% of the data falling within three standard deviations on either side, or a total of 99.7% of the data within those three standard deviations. Now notice that we are not yet at 100%. There are tail values out here that will continue to grow, but the further out you get, you notice it makes a smaller and smaller impact. So most of our work is going to be within this 2 to 3 standard deviations range. So how can we build something to make this look more useful? As we talk about a normal distribution curve, typically our mean value is 0 with a standard deviation of 1. So as we move out from our center, we come to these values: -3, -2, -1, 0, 1, 2, and 3. If you're right of the mean, you have a positive standard deviation value. If you're left of the mean, you'll have a negative one. But how can we take this and interpret it into something more useful when our numbers aren't 0 and 1? Let's take a look. The IQ test is a normally distributed test with a mean value of 100 and a standard deviation of 15. Build the intervals for these standard deviations from the mean for this test. So our mean value is 100, and that's going to go in the middle. And the way the IQ test is set up, it will always be 100. So if the intelligence of the entire planet were to rise, then the amount of work required to get a score of 100 will go up with it. Then 15 is our standard deviation for this normal distribution. So what that means, if we move one standard deviation to the right, we're at 115. If we move 2, we're at 130. 3, we're at 145. Now moving to the left, we'd be at 85 if we were one standard deviation below. We'd be at 70 if we're 2 standard deviations below. And 3 standard deviations below would put us at 55 for our score. So depending on where your score falls, if you have the opportunity to take an IQ test, you would be able to find out where you're at. 68% of the population of the world is going to fall between the scores of 85 and 115. And there's nothing wrong with that. That is where the bulk of the population is going to exist. Now we're going to get out at having 95% of the people fall between scores of 70 and 130. When you reach 2 standard deviations above the mean on an IQ test, when you're out here at 130, that is the technical line of where genius begins. So anything beyond that is considered far above normal and is far enough away that gives special classification for. There's also a special classification for being 2 standard deviations below the mean or lower. However, I do not know that term at this time. So this is how we can take a look at information that's given. What happens when we start looking at data that's already been provided and finding percents of the population that fall to that value? Let's take a look. Here is a standard normal distribution curve for the heights of American males. As you can see, according to this data, the mean height is here in the middle at 69.5 inches. And it looks like our standard deviation is 2.5 inches because we move 2.5 with each step. So what if we were to want to find the probability that a person, an adult American male, chosen at random would be between 67 and 74.5 inches? Well, what we'd have to do is take a look at where this falls on our graph. So 67 is 1 standard deviation below, 74.5 is 2 standard deviations above. So what we would do is we'd take the probabilities of each of these sections, and they were 34%, 34%, and 13.5%. So to find the probability of that somebody chosen at random would fall in this range, we simply add these numbers together. 34 and 34 makes 68. So add another 13.5 to that, and we'd end up at 81.5 inches. So 81.5%, or sorry, 81.5%, not inches, 81.5% of the adult American male population falls between 67 inches, which is 5'5", and 74.5 inches, which is 6'2½". So that is where the bulk is going to fall. Now what if we were to take the same thing and say that in a group of 2,000 adult American males, how many would we expect to find being greater than 6 foot, or also known as 72 inches? How would we find that? Well, the 72-inch mark is here, and if we want to know who falls to the right of that, a couple of things we could do. We can either add up all the areas that are to the right of that, or we can subtract the area to the left. Because we don't know the area out here beyond that 3% from our calculations earlier, here's what we're going to do. We know that half of the data falls below the mean. So we have half, or 50%, and to that we're going to add the section that is not included, and that's another 34. So we're going to take our half and add 34 to it and get 84%. Now what's left is those that qualify for what we're looking for. the area under the normal distribution curve is equal to 1. And it is an asymptotic relationship, meaning that we'll forever fall towards that x-axis without ever getting there. But because we know we have this amount of information, we can then say that 16% of the adult American males in this country are 6 foot tall or taller as we look across the entire population. So different ways of being able to pull information, establish what these intervals are, and pull out the part that we are curious about. Make sure you have the definitions and terms down from this lesson and are ready to use them as we continue a little bit of study in probability and statistics.